Evening, everybody. That was kind of lame. Let's try that again. Good evening, everybody. How's build going? It's the best build so far this year, isn't it? So my name is Russinovich. I'm Chief Technology Officer of Microsoft Azure. Just a raise of hands, how many people have heard of Azure at this point? That's good. It's good to see. Actually, it's not, that kind of question wasn't funny about 5 years ago, so we've come a long way. Now, what I'm going to talk to you about today is not to give you any specific skills to take away as a developer. This isn't something where I'm going to be opening up code and typing things and showing you Xamarin Forms. I'm going to actually take you underneath the hood of some of the things we've been doing in Azure with something called FPGAs. And for those of you that maybe don't know what an FPGA is, I'm going to explain what FPGA technology consists of, and I'm going to explain how it's different than other technologies where you might want to do computing. I'm going to show you where we're using FPGAs today in Azure. I'm going to show you where we're using FPGAs today to power some of our other services, like our cognitive services and Bing. And I'm going to show you the steps that we're taking to make this a platform that will change our cloud into one that is actually multi-layered, and some of the capabilities that you're going to get when we've got FPGAs exposed as a service for you sometime in the future. So our principle with everything we do at Microsoft is first party equals third party, meaning if we've got a first party service that wants to use a technology for something, in this case FPGAs, for example for deep neural networks, we know that third parties can take advantage of that and will want to take advantage of that technology. And so our goal is to bring those things out to the public. And our vehicle for release of those things is, of course, Azure. Now, how many of you know or knew before coming to this session that Azure is already using FPGAs? See, raise of hands. How many of you have used the feature that takes advantage of FPGAs that you know of? So a few of you. How many of you know which feature I'm talking about? So a few of you. Well, so let me show you that feature in action. And that feature is something called accelerated networking. And it's available today in Azure. It's actually been available since Ignite of last year when we announced it. And on certain virtual machine types, you can take advantage of it. And I'm going to show you the difference between unaccelerated cloud networking and accelerated cloud networking. So I'll switch over to the demo machine and show you a bandwidth test. And the bandwidth test I'm going to show you first are two virtual machines running in Azure. You can see they're running a bandwidth meter here. This is the server virtual machine for the unaccelerated test. And you can see that fact by the fact that I've configured this thing with server up here, and it's listening on port 5001. And then I've got a client. Let me go ahead and start the server listening for client connections. And I've got a client here at another virtual machine in Azure that is serving as the client side of that test. And let me start that up. And what the client is going to be doing, it's got a single thread that's pounding as much traffic through a connection as it can to that server. And that server's plotting in real time and printing out at the bottom the average network bandwidth over a 2-second interval. And the numbers are a little too small to see unless you're right up front. But what we're seeing is a little over 4 gigabits per second. So that's not bad, but if you consider the fact that this is a full-size virtual machine sitting on a server with a 40 gigabit network adapter on it, there's a lot of bandwidth left over. And wouldn't it be great if we could have our applications fully utilize that full bandwidth? Well, in fact, we can deliver much more bandwidth by leveraging FPGAs. And I've got the same tests here, except this virtual machine we're looking at is a server that is sitting with it's got accelerated networking enabled, which is taking advantage of FPGAs to offload traffic into basically hardware. Let me start it listening. And then I've got the client here that's going to, again, try to drive as much traffic as it can to that server. We've got our plot in real time. And you can see, if you're up close, that we're achieving close to 25 gigabits per second, which on a 40 gigabit network adapter is extremely high utilization. So this kind of bandwidth that you can get from a single network connection between two virtual machines in a public cloud is industry leading. Now what I'm going to do is take you behind the scenes and explain what an FPGA is that's powering this, and then I'll also talk about some uses of FPGAs, like I mentioned, including exactly how we're doing this with SDN. So one of the reasons that we're investing so much in, let me switch back here. One of the reasons we're investing so much in FPGAs is that there's a data explosion. And if you take a look at how fast data is growing, about every 2 years, the amount of data on the planet is doubling. So if you look, in 2013, there was 4.4 zettabytes estimated total data sitting on the planet. By 2020, people estimate that there's going to be 44 zettabytes of data. And the fact is that we want to get insights out of that data and make use of it, not just have it sitting there, collect your Duck Dynasty downloads sitting there consuming all that space. We'd like to do something more interesting with that data. And that means we want to get low latency because a lot of those insights are in the real-time pipeline. A user makes a request, an IoT device is doing something, it needs a fast feedback on getting insights out of the data so it can respond to that data and take action. And then our services are all scaling out to global scale. Azure and Office 365 are massively scaled systems with huge amounts of traffic and users and applications. And so we need the ability to not just get low latency processing that data, but to scale out and achieve super high throughputs across that data. And we took a look at the computing technologies that we can bring to bear on processing data. You can line them up on a spectrum, where on the left side here, you've got the most flexible computing engines. On the right side, you've got the most rigid. But at the same time, when you burn things into silicon, you can achieve extremely high efficiency. And by efficiency, I mean things like getting really low latency and really great power efficiency. The more general purpose you are, generally the more flexible you are, the more kinds of programs and algorithms you can throw at the compute engine, but you sacrifice in those efficiency. And if you take a look inside of these, well, a CPU, as we all know, has a control unit that's processing instructions. It's got some ALUs, arithmetic logic units, and it's got a register set where it's storing temporary contents of data mutations. If you look at what's underneath a GPU, it's a little less flexible. You can't run general purpose programs on them, but it's got thousands and thousands of processors on it that it can execute in parallel. So it's really great for highly parallel computation. Kind of general purpose, but they're typically beefy and power hungry. And over on the right side, you burn algorithms into silicon. Now you've got no flexibility, basically, because the algorithms are encoded in the wires, and so you can't change them. But now you're not wasting any energy on anything that's superfluous to what the algorithm's supposed to achieve. And so that's the maximum efficiency. And then we've got FPGAs. So I'm going to talk a little bit about FPGAs and why they're in this position in the spectrum, closer to efficiency side of ASICs, but also towards the flexible scale of CPUs. Now, FPGAs, the word FPGA stands for Field Programmable Gate Array. And a field programmable gate array means that it's logic that you can flash and basically program the connections on it dynamically out in the field, sitting inside of a server. So you can reconfigure it to implement different algorithms effectively in silicon. And the way that these make that possible is that they've got thousands and thousands of slices or little blocks that are programmable. And some of the programmable units in these things include basically the equivalent of logic units, which are called typically implemented as lookup tables, LUTs, where you can configure the lookup table to implement custom logic, like a NAND gate or an XOR gate. So very flexible in terms of the logic that you can program into it. They also have arithmetic logic units. They've got static RAM, typically, and where the temporary results of computation can be stored. And they also have DSPs that can do multiplication. And then around the complex, the programmable complex, actually between these blocks, you've got switching blocks, which allow you to program the connections between each of these programmable blocks. So you can create network topologies between them dynamically as well. So you can have data flowing through this thing dynamically, and so create trees, create branches, and all sorts of other data flows on top of this programmable array. A lot of the FPGAs these days also have CPUs, where you can offload some of the computation from a CPU and have it sitting right there next to your programmable blocks. Typically an ARM core is what you'd find there. And then also FPGAs today have connections, like PCI Express connections, so they can directly talk to the CPU complex. They can do DMA into the main memory of the CPU complex, and so very efficient transfer of data from the CPU to the FPGA. Some of them even include Ethernet controllers, so they can talk out on the network. Now, the difference, I think another way to look at this, the difference between a CPU, which is very general purpose, and a FPGA, which is also general purpose, is that the way that they process data is different. With an FPGA, or with a CPU, basically you've got a linear set of instructions that are flowing through the CPU and transmuting data in place. So you can think of the instructions flowing through the CPU complex, processing data in place. Whereas on the FPGA, you can think of it as the data sitting here flowing through an instruction set in massive parallelism. So for algorithms that are parallel in nature, you can program those blocks into parallel streams of equivalent logic, and then just push data all the way through the FPGA, transforming it all the way till you get to an output that you want to expose to the outside world and maybe send that over the network or DMA it into main memory. And so the difference here is the way that you process data, but you get the flexibility here that you don't get with GPUs of being able to program arbitrary algorithms into the FPGA to perform this kind of parallel processing. And so with this kind of architecture, you can achieve enormous benefits in power consumption, because FPGAs consume very low power compared to a CPU or a GPU, but amazing amounts of data throughput, or operations per second, at the same time. At Microsoft, we've been looking at FPGAs, and actually, how many people remember FPGAs back from the 80s and 90s? And they seem to have come, and then they go away, and people forget about them, and then they go off into little niche kind of applications. Well, back around 2010, we had people at Microsoft that started to think, hey, maybe there's a renaissance here coming for FPGAs. FPGAs are getting powerful enough and flexible enough, and the tools are getting better, that maybe we can start using FPGAs as another point in that spectrum of flexibility and efficiency. And so back in 2011, some people on the Bing team, Doug Berger leading that team, went and approached Bing leadership and said, hey, we need to start looking at FPGAs and seeing if we can use them in Bing for index serving, for feature extraction of documents, that we can improve the efficiency of Bing. And so they proposed this prototype board here, Catapult V2. The whole project's been called Catapult. And this V2 board was stood up, and we started to get our hands dirty with what FPGA programming looked like. In 2012, we switched to Catapult V1, the next generation, and we put 60 boards into production as a prototype and actually ported part of the index serve engine of Bing onto the FPGAs, the feature extraction part, to see what kind of efficiencies we get and just how hard it would be to manage these things at any kind of scale. And it looked very promising. So we moved on in 2013, went to a larger scale test, and actually put them into production. So 1,600 FPGAs went into production this year, and we're the core accelerator for the index serve feature extraction. And at this point, we knew that we had something on our hands that really fit this position in the pipeline of efficiency versus cost and performance. So one of the drawbacks, though, of that initial architecture was that we had a separate network where the FPGAs could talk to each other, separate from the network that the CPUs talk to each other. And this created a complexity in our network topologies. And so with Catapult V2, we went with a more flexible design where we put the network inline in the architecture. So we'd plug the FPGAs into servers and then wire the network wire through the FPGA to the actual NIC. And that way we'd be inside the flow of the network pipe. And this offered some other opportunities for us that I'll talk about in a second. Specifically, well, one of them you've already seen is accelerated networking. And so in 2015, we talked to the Bing guys, and we were looking at the challenges we had with SDN, which I'll describe later, on gaining efficiencies and gaining the kinds of performance you saw. And they said, hey, we've got this big FPGA technology. Maybe we could apply that. So we started to look at that and prototype accelerated networking and decided, yes, this was going to fit a need for us in the accelerated networking space for several years at least, as far as we could see. So let's start to get these things out into hardware. And this is one of those places where you got to take a little leap of faith, because we actually didn't have the software ready yet. We hadn't figured out how to operationalize these things yet, but we knew that once we had the software ready, if we didn't have the FPGAs in the data center, that we'd now have to wait to get those FPGAs deployed. So we thought we'd go in parallel. And starting in late 2015, we started putting FPGAs inside of every single one of our servers. The FPGAs we put in are from a company called Altera. How many people have heard of Altera? So Altera is a company that's been making FPGAs for decades. Intel purchased them in 2015, and so they're now an Intel subsidiary. The Stratix 5 are the FPGAs that we started to deploy in our data centers, and in 2016, we got the software was done, and like I mentioned, at Ignite, we launched accelerated networking and made it available to the world, just like you can take advantage of right in those VMs that I showed you here in Azure. Now, the Catapult V2 architecture, as I said, has the FPGAs wired inline in the network. And so if you take a look schematically at what a server looks like, here's a Windows Cloud Server version 2. We're up to version 6 of that cloud server architecture, by the way. But when we launched Catapult V2, you can see that there's 2 CPU complexes here. There's PCI Express lanes, 8 of them, connected to a real network traditional network adapter. You can see the Catapult V2 FPGA there with its own DRAM, the FPGA programmable locks there, inlined in the network. So you see the network coming in from the left. It flows through the FPGA and then flows out into the network adapter of the server. And there's also channels, 2 PCI Express 8-channel connections to the server. So we also have roughly 16 gigabits per second of gigabytes per second of throughput from the FPGA directly into the memory complex of the CPU. And so this topology is actually the one that we decided to go into production with because it's so flexible. You can see because it's inline in the network, we can use it for accelerated networking. You can see that because it's got this very high bandwidth connection to the server, we can use it for other things like accelerated computation. By offloading things and algorithms from the CPU into the FPGA, we can also use it, for example, for accelerating the storage devices because of this high throughput bandwidth. So we can do things like crypto offload for storage devices or CRCs for storage devices in the FPGAs. Now, this is an actual picture of the Catapult V2 card. It's called a mezzanine card, and it sits in the blade chassis. As you can see there, there's 2 of them here in this particular schematic. Actually, this looks very much like the blade that I used to use for a while myself instead of my laptop. And I'd take it to Starbucks, kind of interesting. I'd take it to Starbucks, and people would give me really weird looks when I plug it in. And I can only assume that was jealousy on their part that I had this thing. But after a while, it got a little heavy, so I've switched to a traditional laptop. Now, let me switch and talk about more detail about the FPGA and software-defined networking and how that works. First of all, in Azure, if you're not familiar with Azure Networking, the core of it is something called a virtual network. And this is where you can create a private network for a group of services, including virtual machines, and connect them together. And you can overlay an IP space of your own. So this is the way that you might want to have them talk on a private network, not visible to any other services, any other customers' VMs, not even your own VMs that are in separate virtual networks. It's basically a network bubble. You can set ACLs on the virtual network so that it only allows certain kinds of traffic in and out of the virtual network. You can also define custom routes with user-defined routes so that you can have traffic flow, for example, from your virtual machines through a network virtual appliance before it exits the virtual network and goes someplace else, or as a DMZ device between two parts of your virtual network, two subnets. We also have services that are more customer-facing, like bring your own IP addresses, reserving IP addresses, load-balanced IP addresses, IP ACLs, load balancing, and DNS services, plus DDoS protection. And then we have connectivity for hybrid, where you can connect your enterprise network through VPN gateway or through an exchange or network service provider through direct connection into our backbone, a feature called ExpressRoute. All of these features are implemented in software-defined networking. And what do I mean by software-defined networking? If you take a look at traditional networking, it's in IT networking, it's been these big boxes. And these big boxes have all the networking logic in them. They've got a management interface where you go and tell it with high-level abstractions how you want the network to look and how you want it to behave. Then underneath that, there's basically a control layer that is taking that and processing it into low-level primitives and then implementing it on the data flows that go through that device. And these are typically appliances. They're very expensive. They scale up, and they've got a problem. They don't scale out, and they're susceptible to failures, and so that makes them non-scalable for the kinds of scale that we get to in a modern cloud data center. So the only way to do networking in the modern cloud data center is with software-defined networking, where you take these layers and you split them apart and implement as much as you can in software. At the top, in our stack, we've got the Azure Resource Manager control plane that lets you program network, create virtual networks, create load balancers, set network security group rules. All of that is translated underneath that API surface into controls, these low-level control commands that controllers, like the Software Load Balancer Manager or the Virtual Network Manager, Regional Network Manager, would translate into primitives that are implemented at each host, where each host serves as part of the distributed network fabric. So down at the host, for example, if you say this virtual machine is part of this virtual network, that's where, as the network traffic flows in from the outside, there's packet encapsulation and decapsulation, snatting, denatting that happens before the virtual machine gets the packet. And by the time the virtual machine gets the packet, it looks the way the virtual machine would expect it, like it's coming from another virtual machine in its own private IP space, even though underneath there's the Azure IP space that's invisible, that's actually where packets are getting routed through routers in the network. So you can think of this as pushing the network logic all the way down to the servers, and that's where you get the kinds of scale that's necessary for the public cloud. If you take a look at a server itself, we've got a component inside of that. It's performing that kind of logic I just described. It's called a virtual filtering platform. And it's like a virtual switch inside of the Hyper-V network stack. So a virtual machine is talking out through this virtual network stack, and sitting in here, looking at the packet flows, is this component here, which logically consists of different layers of rules. And these different layers of rules apply the logic for whatever controller they're associated with. So for example, you can see here we've got 3 layers shown. At the bottom is SLB, where natting happens. And the SLB stands for Software Load Balancer. And Software Load Balancer is a feature in Azure where you can go set up a public IP address or an internal IP address and have it be load balanced across multiple virtual machines. With a public IP address, the virtual machine, the traffic coming from the outside the internet is aimed at a public IP address, but it gets routed into a physical IP address inside of our data center, and it gets translated into a virtual network IP address that is bound to that public IP address. And so all of that logic is implemented in that layer right there. When a packet flows out from this virtual machine, instead of looking like it came from the customer's virtual network IP address or the Azure physical IP address, it looks like it came from the public IP address. And that is implemented in that component right there. This SDN stack, by the way, is the same SDN stack, this virtual filtering platform, that we put inside of Azure Stack. So this is also what we deliver in our on-premises extension of Azure. If you take one level look deeper to see how those layers are implemented, they're implemented with a technology we've developed called flow tables. And these flow tables are really just tables of rules that are processed one table after another with a set of rules that specifies what should happen to this network packet as it comes through. If it matches any rule, then maybe some transformation happens. And you can see here, these three layers, virtual network, load balancer, and IP ACLing, or the network security group rules, all have some example rules there. Just taking a look briefly at the load balancer ones, you can see that any traffic that flows to 79.3.1.2, which is a public IP address that we might assign you to your software load balancer, if it's coming out of the virtual network and aimed at that, then we destination NAT it to 10.1.1.2, which is the IP address of that virtual machine. Similarly, if the traffic is inbound to any of those IP addresses in that virtual network, in that subnet, then we DNAT it to that public IP address. So the virtual machine, it believes that traffic is coming from that public IP address. And that is the way that virtualization of the load balancer IP address works. And you can see ACL rules there, and then you can see the virtual network rules there with some user-defined routes, like express route gateway right there. There's encapsulation to send the forward traffic to the IP address where we've got the gateway to route traffic to that. You can see that there's also encapsulation, decapsulation to other IP addresses of other virtual machines that this virtual network is talking to. And so these set of rules is exactly what happens to every single packet that flows between one virtual machine or from the internet to a virtual machine and back. Goes through these flow tables. The controllers are what programs this, like I said. So when you go and set up a virtual network and you set up a virtual network routing policy with, for example, those user-defined rules or specify your gateways, the controller goes in, sets up those rules in the flow table, and propagates them out to all the virtual machines, or all the servers that have virtual machines that are part of that virtual network so that they know how to process those packets. And when you create a tenant, meaning you create deployment of a virtual machine, for example, with an public IP address and a load balancer, that's where that is flowing down into the load balancer layer or the ACL layer with those rules that get created in those tables right there. So again, Azure Resource Manager is where you'd actually create a load balancer, gets down into a controller, which is going to figure out these rules and go program the VFP flow tables to implement those rules. The challenge that we started to see coming at us in 2010 when we started to talk to Bing about FPGAs was back then we had 1 gigabit network adapters in our servers, which most of the industry had. We knew 10 gigabit was coming very fast, and we knew 40 gigabit was right after that. And like I mentioned, we've got 40 gigabit network adapters in our servers today. We know 50 gigabits upon us, and 100 gigabit is just a little ways out. And if you take a look at the computational power to process those flow tables at that kind of throughput, you're burning cores of expensive processors. And those cores that you're burning have two effects. One, it increases the latency of the packet processing, because all of these complicated rules flowing at that rate, competing for cycles on CPUs, means that you're introducing latency into the network, and you're not going to get native type networking. The virtualization overhead is going to be very high. And the second problem, of course, is that those cores that we're burning for the network, we can't sell to do what they should be doing, which is general purpose processing for virtual machines. So we thought, and we also saw that the software-defined networking stack continues to evolve, and so we couldn't just go to the network adapter manufacturers and say, burn this logic into your NICs for us, because it would take a while for them to produce those NICs with that hardwire logic, a year to 2 years. And by the time they did, our software-defined networking stack would have changed, and those NICs would be obsolete. So we looked at FPGAs and said, looks like this, we can reprogram them to implement our software-defined networking stack and have the flexibility that as that stack evolves, we can just reprogram them. And so that's where SmartNIC was born. And like I said, back in 2015, we started to deploy FPGAs in preparation for us deploying SmartNIC software onto them. The FPGAs used to implement those flow tables on them. And today we're using them for this network offload for virtual machine software-defined networking. We also see in the future potentially putting crypto operations in them, using these FPGAs for storage acceleration like I mentioned. But this first step is software-defined networking. And if you take a look at what happens now on a server with software-defined networking, we take the controller APIs send the rules down to the server, and we compile on the fly these generic flow tables, or GFTs, into format that the FPGA program understands. And that FPGA sits there and processes those flow tables in the software-defined networking programs that have been flashed into the FPGAs. And you can see here some of the other things that we're looking at: quality of service, crypto operations, and even RDMA, of implementing those also inside of this SmartNIC, where you see 50 gigabit network, which is the next thing that's coming in our data centers, wire coming in, flow tables processed there in the FPGAs, these other services as well, and then the traffic flowing up into the virtual machines. They flow up directly into the virtual machines using SROV. So these FPGA devices project virtual network adapters into the virtual machines themselves, so the traffic bypasses the host altogether. So now with this, zero CPU overhead for data flows, unless there's changes to the rules. There's zero usage of the CPUs for the software-defined networking, and the latency now is just the logic inside the FPGAs to process these packets, which is much closer to ASIC type burning in the software-defined networking rules than implementing them on a general-purpose CPU that isn't optimized for data flows like this. And if you take a look at the comparison between our older unaccelerated network and the accelerated network, the big change, of course, is that the virtual switch is sitting there inside the server doing all that processing on the left. On the right side, we've got SmartNIC, where all this stuff has been offloaded. I opened this talk by showing you a dramatic representation of the kinds of bandwidth performance improvements we get by offloading off of the CPUs. We've got, like I said, the fastest cloud network. Fastest in terms of throughput, where you saw close to 25 gigabits per second. We also have the fastest in terms of latency. So let me go switch and show you network acceleration with latency test instead of a bandwidth test. So for that, I'm going to go back to the unaccelerated VMs. Whoops, didn't mean to do that. And I'm going to run a different test here for latency. This is the server, and over here is the client. And I'm going to point this client at 10.0.0.5. I'm going to run the test for 5 seconds to see what the latency looks like. And we're going to do a TCP latency test. So this is over the unaccelerated network. Oh, yeah. Who knows what VM I was talking to there? I hope I didn't disturb it. We should be seeing about the same thing because that's another virtual machine on the network, on the virtual network. I just happen to have a valid IP address on my subnet. So 145 to 200 microseconds is the kind of latency you see. Not bad, but what do you think we'll see with the accelerated network? Anybody have a guess? 2? No, okay. Let's be reasonable. So here's the server. And this one is 10.8.0.11, 5 seconds. Drum roll, 30 microseconds. So roughly a 5x, 6x, somewhere in the neighborhood of 5 to 10x reduction in latency. And you want to get any lower, and you're talking about dedicated network wires and RDMA. And so this is over pure Ethernet, just with offload from the CPU into the FPGAs. But you might be saying, hey, Mark, all right, so that's a nice synthetic test. How about something more real? How does this affect an application? So I've got an example of that set up here. This is a SQL Server client that's hitting a SQL Server, again, over unaccelerated networking. And this is showing you that what we're doing is bringing this acceleration technology into our back-end services. So if you're talking from an accelerated network virtual machine all the way to an accelerated network back-end, you're going to see the dramatic effects of accelerated networking as well. And here, the unaccelerated network, pointing at an unaccelerated SQL server, Azure database. You can see the latency of just a query operation, simple query on the database, is at 1.2 milliseconds. So there's, of course, application logic overhead that we didn't see in the previous example. And now here's the accelerated version. You can see we're about 300 microseconds again. So this is the kind of effect you're going to see on your applications. And what's coming here is this is the ARIA 10 device from Altura we've already announced at OCP 2017 as the FPGA as part of our Open Compute Platform Generation 6 server, codenamed Project Olympus. So this is giving you an insight into where we're going with FPGAs, 50 gigabit networks in our Gen 6 servers, and this much more beefy FPGA. So that's a look at how we're using FPGAs already in Azure. But we're using FPGAs in other ways across Microsoft. And by showing you this, I'm giving you a taste of where we're going with Azure and making these FPGA technologies available to you. Of course, one of the huge topics here is intelligence everywhere. A key part of intelligence everywhere is machine learning. And a machine learning algorithm that is useful for all sorts of different scenarios is deep neural networks. Deep neural networks are used for computer vision, language translation. If you took a look at the Cortana Intelligence suite of APIs, you're going to see examples of all of these different kinds of scenarios, and they're all based on deep neural networks. And deep neural networks, by the way, for those of you that aren't familiar with the concept of deep neural networks, you've got an input layer. You've got basically something called layers. Your inputs come in. They're represented by the nodes here on the left. Your output's over on the right side. Your output is what you want your answer to be. Is it a cat, for example? Your inputs are images represented in mathematical forms like vectors. And then you've got lines connecting these nodes in the middle. Those are called hidden layers because they're between the input and output. They're not visible from the outside. They're just mutating values as they go through. And each one of these lines is given a weight, and each node also has a bias, and then there's a function that you process on the node that takes those weights, multiplies them by the input values, and adds the bias, and then performs that function, and then passes that value out the lines on the other side of it, which are, if they're a middle layer, to another layer, which is also then applied a weight plus a bias, and the same step continues. And the way you train these things is you give it a set of raw data, training data, and then you know what the answer should be. And when the neural network gets the answer wrong in mathematical form, you apply a mathematical algorithm to try to figure out how to get it closer to right and use a process called backpropagation to go fix the weights up back deeper in the layers as you go. So for example, from image recognition, what happens, and this is a special type of network that's optimized for image recognition called a convolutional neural network, or CNN, optimized to do kinds of little feature extractions purposefully. So one layer might end up being able to figure out what eyes look like and mouths look like. The next layer figures out what parts of faces look like. And then the final layer actually puts them all together and knows what a face looks like and then can do facial recognition. You might be saying, what's a deep neural network? Because that's all anybody talks about anymore. What's a deep neural network? Anybody know what a deep neural network is? Blair?
Any neural network that has many hidden layers versus few.
That's right. Where many might be one, just because you want to be cool and say you've got a deep neural network. So nobody, it's one of those things like, what is a deep neural network? Well, you know it if you see it. Or if you want to tell people how cool what you're working on is, you've got a deep neural network. Let me show you image recognition in action. Let me switch over here. And there's a project that is aimed at classifying the shapes of galaxies. What we discovered, I guess, sometime in the last decade or so, is that the number of galaxies in the universe is way bigger, way more than we ever imagined. There's something like 2 trillion of them that we estimate. Obviously, no humans are going to go classifying and labeling 2 trillion galaxies and figuring out what shape they are. So this is where neural networks come in, automatic recognition of galaxy shapes. And this is a project that was started by Jim Gray, who's a famous legend in the worlds of transactional databases, worked at Microsoft until he sadly disappeared on a boating accident a few years ago. But this project he started before he disappeared, and maybe he's up in one of these galaxies now, but he basically said we can apply deep neural network image recognition to galaxy, figuring out galaxies automatically. And so I've got a folder with a whole bunch of galaxy images, and you can see there's like eye galaxies. This is called the eye shape. No, I'm just kidding. That's not the eye shape. This is elliptical galaxy. Let's go classify some images and see other shapes of galaxies. And I'm applying convolutional neural network here to do galaxy transformation. You can see that there's different types of elliptical EI, elliptical ER, spiral, 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 spiral. This is the code behind what I just showed you. There's a .NET library for neural networks here, and here's the definition of that CNN that's doing this processing. And then here's where we set up what are called the hyperparameters, which are the parameters that have nothing to do with the model, but the way that you train the model, like the number of iterations and the size of the data set, and whether you're doing acceleration or not. And so what I just showed you is just GPU-based acceleration. By the way, I thought this was kind of funny. I said, maybe I can fool the neural network by giving it images and seeing what it would come up with. So I created a couple of images here. Well, actually, one of them I already had. By the way, this one is a picture that, it's a little known fact, but I auditioned to, I needed to raise some money to support my sysinternals development. So I auditioned to be the spokesperson for a Japanese soda brand. And it's actually a soda brand called Hageshi Kumo, which means fierce cloud. So I thought it was really appropriate. Now, unfortunately, I didn't win. Scott Guthrie got the job, and so I decided to write books instead to earn money for sysinternals. But now, if I go take a look, this is how smart the neural network is. So it classifies me as unknown aliens. So I wasn't able to fool it, unfortunately. But I had fun with the pictures. So now, what is the benefit of FPGAs with deep learning? Well, first, you get tens to hundreds of tera operations. We call them tera operations because they're not necessarily floating point as we know them. There can be single precision or half precision floating point. So you can get really effective inference, which means the scoring like we just did, with very low batch sizes. With something like GPU, because there's such overhead pushing data into the GPU, the only way you can do anything efficiently is push tons of data into the GPU and then have it do stuff. With FPGAs, you can trickle things into the FPGA and basically do streaming inference. And you get ultra-low latency. It's about 10x better than CPUs and GPUs in terms of the performance and efficiency of wattage per operation. It's flexible because this space is evolving so quickly. Even in the space of neural networks, it's evolving very quickly. But there's all sorts of machine learning algorithms you can program into FPGA. And then finally, we can get massive scale with a fabric like we've got, where we've got FPGAs and a whole bunch of servers. And that's what I'm going to talk more about here going forward. But let me show you, I've already started to apply, like I told you earlier, neural networks to inference for Bing index serve document recognition. And you can see here, when we put it into production, the kinds of performance improvement we saw. And this scale here on the left side is just it's gone for competitive reasons. But you can see that software is significantly slower than FPGAs in terms of the latency for this inference. And every bit of this helps people, figure out when they type a search engine query like, where can I get a haircut like Joe Belfiore, how to get that answer as fast as they can. This is what we saw when we actually put this in production. And this was kind of interesting. It kind of scared people when we first turned it on in production in Bing. That bottom is the average FPGA query load. You can see the query load spikes just like the spikes higher. Well, actually, let me talk about the top side. You can see the top side, basically the same kind of performance improvement we saw on that scatter plot over on the left side. You can see that at the bottom, though, what we saw is the load started to rise when we turned the FPGAs on. And this freaked people out because they were afraid that Bing was going to tip over, and they also were like, why is the load going up? It should be going down because these things are much more efficient. The answer is that Bing has a global optimizer, and when it sees queries per second, when it sees the utilization of servers go down, it starts to send more queries to those data centers and those servers. And so what was happening was it was being able to throw much more queries at these servers that were excited with the FPGAs, and that caused the utilization to spike. So it was actually the system behaving as it should be, just was a little bit unexpected. Now let me show you a real live demo of FPGAs versus CPUs. And to do that, I'm going to come back to this machine and open up a browser to a little app that we've got. Now this is going to do, basically, it's like Bing Inference. We've got a whole ton of documents, and those documents have the word Bing in them. And I've got 3 test configurations here. The first one is a single CPU. I'm going to fire that up. And what this is doing is showing you how fast it's able to go and process documents. And you can see the latency also that it has in coming back whether a document has this search query in it or not. In the API, you see it's about half a second here, about 500 milliseconds. Here, this test is 24 CPUs, so it's a full server, about 300 watts of computational power. You can see because this is a parallelizable workload, I'm able to get it much more throughput. And at the same time, I've also lowered the latency because there's less contention. This is about a 40x improvement in throughput over the previous one, and about an 8x improvement in latency. But now when I go throw it at 24 FPGAs, this is about 150 to 200x improvement over the CPU, and it's about a 50x improvement in energy savings. And so this is actually what we're taking advantage of in Bing. So where are we going with this? We've taken some next steps in Bing. Besides this kind of small-scale, fixed-purpose FPGA acceleration for something like IndexServe, we're looking at having a much more general platform for FPGAs. We call it hardware microservices. So what are hardware microservices? We consider hardware microservices to consist of 3 things. At the core, of course, is FPGA hardware. But you have to have that FPGA hardware wired directly to the network so the FPGAs can talk to each other without going through a CPU complex. So for ultra-low latency, sharing data, maybe a pipeline or one service calling another service directly. And you need a management fabric to go and manage the FPGAs and programming those FPGAs with applications that are being delivered dynamically. If you take a look at this picture, you can kind of get a sense of what this hardware microservice fabric really represents. Here we've got the traditional scale-out server architecture, and we've got some of our deep neural network algorithms programmed to execute on a subset of them. I know this looks like aliens trying to clean an air conditioning filter, but that's what it's supposed to be. Now, when we put this logic in FPGAs, we basically lifted the whole computation off into this other layer that's directly connected to the network and programmable directly through the network to deploy microservices into it. And so you can see now this fabric has web search ranking, deep neural networks, SQL acceleration, SDN offload, all programmed into it. Potentially executing completely independently of the CPUs that those FPGAs are attached to. The CPUs, if they're actually attached to them, are simply serving as conduits for offloaded computation acceleration of algorithms that are primarily acting on the CPU. But in fact, with this kind of architecture, you don't even need CPUs connected to the FPGAs because you can deliver applications directly through them through the network. Now, benefits of this kind of architecture is you decouple the CPUs from the GPUs. If you've got GPUs that are sitting there fixed on CPUs, and the only way to get to them is through the CPUs, and you basically allocate your services to the CPUs, then you can end up with fragmentation. You can end up with a case where the application offload requires a certain number of FPGAs, but very little CPU, and now you're burning a lot of CPUs doing nothing because you're consuming those FPGAs attached to them, and you've got this tight coupling between the two. You also, with this topology, can oversubscribe the FPGAs or share the FPGAs. In a case where you have services with dedicated servers with those FPGAs attached to them, you can't take those underutilized FPGAs and use them for something else without some complexity in your compute fabric. But if you can treat those FPGAs as resources that you can plumb other algorithms into, other software into those unused parts, then you can maximally utilize those FPGAs. And then finally, you can expose different accelerators to a service. And what I mean by different accelerators, it means different types of acceleration, like deep neural network acceleration or some other kinds of acceleration, other different kinds of machine learning algorithms, all exposed to an application that can then call on all of these services through the network. And if you take a look at the way that we're doing this for DNNs, is we take the deep neural network, the pre-trained deep neural network model, and we take those neural network layers, those functional units, and push them down into FPGAs independently. They don't have to be on the same FPGA, so each layer can be on different FPGAs, but the way that they talk to each other through those weights is through the network. So now we've got massively scalable DNNs independently scaling from the CPUs, where the deep neural network is basically laid out across this fabric of FPGAs. We've already started to deploy this in Bing. We've already got this in production in Bing as part of our acceleration, the next level of acceleration for cognitive services training, as well as for Bing index searching, index ranking. And this is just an example of some of the benefits that Bing saw when they switched to this versus the hardwired topology that they had before, that I described before. In that hardwired topology, the scale unit was an FPGA, full FPGA. But when we moved to this hardware microservices model, you can see that we could actually scale the CPUs and FPGAs differently. And so that index serve, their DNN, required all of those FPGAs, but because we could pack them now, those instances, into FPGAs using this hardware microservice model, we could fully utilize those FPGAs, and now we don't even care what the CPUs are doing. That's just the CPU backend, basically, management of the whole thing, scaling independently of what's going on in the machine learning layers. And so we saw immediately an efficiency gain of 73% on the utilization of the FPGAs that we had deployed, leaving room for other things, like other DNNs. And so our cognitive services are being trained on those FPGAs now. And what we're also working on, and this is in flight, is the ability to take a DNN model and then dynamically say whether you want it to compile to TensorFlow or CNTK or some other machine learning framework, come up with a generic low-level representation, and then push that into FPGAs. And you can see that DNN being decomposed into those units and then being pushed down and spread across FPGAs like the way I described. This gives you the ultimate flexibility on your models, being able to go and push them to GPUs or FPGAs or CPUs, but have them dynamically compile down and be able to target FPGAs. And so this is a picture of what we've got running in Bing now as the architecture. You can see that there's a high-level, the beginnings of it anyway, of what we've got here. A high-level resource manager, an FPGA manager that's keeping track of the resource allocations on those FPGAs, those black boxes. Service managers, which are responsible for deploying the compute part of the services that are utilizing those FPGAs. And you can see I've got a couple of them represented here. One's a ranking service for the index ranking of index serve, and the other one's Azure Data Lake Analytics, which is looking at pushing machine learning also into FPGAs. And then you can see that now we're able to spread the FPGA microservices across the FPGAs, again, independently of where the services are running on the CPUs. This is what we really want to bring into production in Azure. There's a ton of work here, so I can't give you any timelines, but I can tell you we're actively working on using this in production internally. Some of the problems that we've got to solve here is are the same kinds of problems we had to solve in creating Azure as a multi-tenant service as opposed to an IT infrastructure service. Really, this is what we've got running in Bing is really IT infrastructure of this. It's not hardened against multi-tenancy. It's not got the most efficient resource allocation in it. There's security issues with the way that the FPGAs are programmed right now. We basically don't have partial reconfiguration yet implemented, where if there's multiple hardware microservices, we need to recompile them all together and reprogram the whole FPGA versus just recompiling parts of the FPGA. So these things we're working on, and once we solve them, once we get this engineering work implemented, this will become basically the realization of what I represent in the title of this talk, which is we will have what we consider to be a fully configurable cloud. And if you take a look at what we mean by fully configurable cloud, there's the compute layer that we know, all the servers in the data center, and this is where you run your general purpose compute jobs. There's the reconfigurable compute layer, which is basically hardware programmable through FPGAs. And at the core of everything is our converged network. By converged network, I mean there's no separate network for the FPGAs. These are sitting in line on the network fabric of our data centers. And so compute, FPGAs can share the network. Whoever needs to be allocated network bandwidth gets it. These FPGAs can talk to each other directly without needing CPUs. And we believe that if you take a look at the kind of scale computation you can get for those kinds of algorithms that I've described that fit really nicely on the FPGAs, this is basically the core of an AI cloud, where we could, with FPGAs in hundreds of thousands, millions of servers, throw massive machine learning problems at this thing and get ultimate efficiency out of this kind of topology where we're not being slowed down by overheads that are unnecessary, like CPUs, and we're getting close to hardware-type acceleration on these kinds of problems. So that brings me to the conclusion of the talk. I think what I hope you take away from this is the fact that this FPGA stuff at Microsoft is real. We've been working on it for a really long time, which is ages, hundreds of years in cloud terms, back when we started looking at this in 2011 with the first Bing prototypes. And now we've got this thing out in production at massive scale. Like I said, every single server in Azure since towards the end of 2015 has an FPGA inside of it, and it's in operation delivering the world's fastest cloud network already. And then we're on the next phase of this journey of creating this configurable cloud inside of Bing with this microservices platform that we're going to bring out over time to Azure. And already all of this is, besides supporting Bing, cognitive services as well, of course, like I mentioned. So you're already indirectly feeling the benefits of this kind of platform as you use things like the cognitive services that we've got and the other machine learning features of our other applications. So with that, I want to thank you very much. I hope you had, this was an interesting talk to you. I know that this isn't like something you can walk back and type new programs in using, but hopefully you did maybe learn about a feature in Azure that you might not have been aware of that you can start taking advantage of. You've got to go opt in right now to accelerated networking because there's potentially very extremely rare application compatibility issues with taking advantage of SROV from applications. But we've not seen any problems in anybody in production. So recommend if you're on any of the larger VM sizes, you can take advantage of accelerated networking now and get that kind of performance that I showed you on the largest full server virtual machine sizes. So with that, I want to thank you very much for coming. Hope you have a great attendee party tonight. I hope you had a great build. And thanks for supporting Azure. Thanks.